Perfect. So we're going to have now Brian Swingle, who is in Brandeis. He's going to tell us about hydrodynamics and the spectral form factor. So thank you, Brian.
All right, great. Nice to see you all here. Hope you're all doing okay during these rather chaotic times. Thanks a lot to Hugo and Masamichi for organizing. Thank you all for being here. And yeah, today I'm going to talk about quantum chaos, specifically about two different manifestations of quantum chaos and how they're related. So I'm going to talk about hydrodynamics, which is sort of the physics of the slow dynamical modes of the system related to energy conservation, for example. And then the spectral form factor, which is really a measure of the fine-grained properties of the energy eigenspectrum. And the big picture is that we know quantum chaos has many avatars. Perhaps the most direct avatar is that you have some system in the lab and the system forgets where it came from. It loses memory of its initial condition as it evolves. That's one of the hallmarks of chaos. And another manifestation may be that it has some kind of so-called conventional or normal transport, which means, say, diffusive transport, as opposed to ballistic transport, which you might think occurs in an integrable system, for example. And then there are, of course, more elaborate notions of chaos. For example, there are echo-like experiments where you try to reverse time in some sense. This is also related to out-of-time order correlators. And these are trying to probe aspects of a quantum butterfly effect. And then there are even sort of more fine-grained notions related to the detailed properties of the spectrum of energy eigenvalues. And these physical phenomena typically co-occur in many situations that we want to think of as sort of intuitively chaotic. But it's not clear a priori how they all really relate to each other. Whether you can have one and not the other or something like this, or what the time scales are that relate them and this sort of thing. Okay. So this talk is about connecting some of these things. It's specifically connecting hydrodynamics to the spectral form factor. It's based on a paper that I wrote at the end of last year with my student, Mike Weiner, who led this project. So, and it's the observable we're thinking about is this, again, the spectral form factor, which is defined as follows. I'll give a more elaborate definition a little bit later. But we take the time evolution operator, U, for a time big T. Big T is always going to be the time, never the temperature. I compute its trace. I square that or take the absolute value squared, and then I average that over some disorder. In fact, that disorder could maybe even just be averaging over the time a little bit, over the time T. But let's say there's some small randomness in my system. It could have intrinsic randomness like SYK, or I could just add a small amount of randomness to the Hamiltonian, an amount that's so small it doesn't change the dynamics very much, but will affect the fine-grained energy properties. And I'm going to average over that disorder. And what that does is produce a nice smooth function of time called the spectral form factor. If you don't do this averaging, it looks very erratic. I'll show you a picture in a second. And here's kind of a picture of it. You just have these two contours, a forward contour and a backwards contour, and you take the trace. So you identify them via the blue dots and the red dots. And the hallmark of chaos in this system, of quantum chaos, is that at some intermediate time, the spectral form factor is just linear in time. And this is also what you find for random matrices. And so the question is sort of under what conditions is this random matrix behavior realized in physical systems, like in, in some local Hamiltonian that you actually care about in the lab. So I just want to make you aware, I'm not going to really discuss this in any detail, but there's a lot of prior work on this topic. In particular, in the sort of old school quantum chaos literature, connection between transport properties and random matrix theory was made at least as early as this work of Altshuler and Shklovsky, where they pointed out that if you had some single particle, like quantum dot, basically, that once you went past the diffusive time scale, then you'd find that some certain counting property looked like that of a random matrix. And you can find a nice review of some of these things in this more recent paper from a couple of years ago. In the many-body context, there's been a lot of nice analytic results recently. Vedika already mentioned this Bertini-Coase-Prozin thing, where they were in a kicked Ising model able to derive analytically the spectral form factor. Many of you here are probably familiar with the work of Saad Shenker Stanford, where they also derived this for SYK. And there's quite a few other works, as well as a large number of numerical studies using exact diagonalization. There's also specifically people who have looked at the onset of random matrix behavior, like how it arises out of the sort of detail, so to speak, or the the particular peculiarities of the given system. I'll mention some of this a bit later. And then when I talk about hydrodynamics, what I'm actually going to use ultimately is this theory of fluctuating hydrodynamics that's been developed in the last 5 or 10 years. And I'll specifically focus on a simple theory discussed by Chenlin, Delecresse, and Hartnell, which is about energy diffusion. So you'll see that appear later. So this is an incomplete list, but just to give you a flavor of what's going on here. So let me first remind you about chaotic dynamics and random matrix theory. So here's random matrix theory. You have a random matrix H, you have a potential V, and the probability of the matrix H is proportional to the exponential of the trace of this potential. This is one class of random matrix problems. And because it's a trace, this reduces just to a problem of the eigenvalues. And there's a famous calculation that you can do, which shows that there's this eigenvalue repulsion factor here with a factor of bold beta, which is the so-called Dyson index. And there's lots of ways you can probe this. The simplest thing you can do is look for the density of eigenvalues. That's like the 1-point function. The next simplest thing would be to look at the 2-point function. That 1-point function is interesting and is certainly physically observable, but not so universal. Whereas the 2-point function, the correlation between pairs of eigenvalues, is actually quite universal. And a conventionally convenient way to package this information is in terms of this spectral form factor that I already indicated. So here again, you see I'm tracing time evolution operator. Now I'm including what I call a filter function, which lets me select parts of the spectrum if I want. This is convenient for a variety of purposes. And then I'm doing the disorder average, which is the overbar. And on the right here, you see a picture of the kind of typical behavior. At early time, there's what's sometimes called a slope, some kind of rapid decay on a short time scale. And then you see that after a relatively short period of time, you have this very long, very linear ramp behavior. That's the random matrix ramp. And then at exponentially long times, you have this so-called plateau. So I'm not going to think about the plateau at all. You just forget about that. I'm going to talk about the ramp and how the ramp emerges out of the details of your many-body system. But just a word about the filtering. You often, well, so at the top I've written the formula from random matrix theory for this spectral form factor. You see it's linear in time. The Dyson index appears, and then this filter function appears with an integral over energy. It's common in the literature to see people consider the case where this filter function is e to the minus beta h, and it's called a thermal spectral form factor. That's fine and interesting. I just want to make the point that it's not concentrated around that particular temperature. There's no entropy factor here, so it actually still knows about the whole spectrum. And if you really want to zero in on a certain set of energies, it's nicer to use a Gaussian filter, where you explicitly pick out a band of energies around some E bar with sigma. And then if you plug in the random matrix result, you get a prediction for what the spectral form factor with this Gaussian filter should look like. You have the Dyson index, the time, and the width of the energy band. And the claim is this particular number with this width that you control, the time and the Dyson index, which is just related to the symmetry, this is like a hyper-universal thing. Almost any, well, you can look both analytically and in a large variety of numerical studies, and you'll find that this is exactly the coefficient at sufficiently late time. Okay. So I'd really like to understand where that comes from or relate it to other properties of the system, and to also understand how this behavior is approached again. Let me introduce an important notion, which is the Thoughtless time. This is just defined as the time for the system to come close to the pure random matrix result in the spectral form factor. To be precise, I'm going to consider this connected SFF. So I'm going to take the spectral form factor and subtract the disconnected part, which is just the average of the time evolution operator whole quantity squared. So this is like going to decay to 0, and then this connected part will give you a nice clean ramp. That's what's shown in the orange line here. And again, I'm only interested in the ramp part. And this Thoughtless time is just going to be defined, again, as the time required for this connected part to be close to the linear ramp result that I have here. And what close means, you'll see later. I mean, this is something we can choose, and the Thoughtless time depends on the notion of closeness. And I'll mention again that this has actually been looked at numerically in a spin chain, well, in a variety of contexts, but in a spin chain by this paper of Garibian et al. In 2018. And then also it was studied in a flow K model by Friedman et al. In 2019. And in particular, they had a large Q limit where where Q was the number of states on each site. And in that limit, they could actually analytically establish the existence of this ramp and also understand what the Thoughtless time is. We'll actually rederive one of their results in a second. So the goal, again, is we want to understand these different time regimes and how general they are and what controls the crossovers. So like once again, the times, we have a very early time where things are very non-universal. Also all the details, what the dimension of space is, what kind of degrees of freedom you have, what the scattering times are, that all matters here. I don't want to talk about that. Then there's a later time scale, which I'll call the hydrodynamic regime. This is the regime where all the fast things have decayed and all the slow things are still going on. And in that regime, we can hope for a quasi sort of universal description. That's one of the things that I'll tell you. And then we want to see how the ramp regime emerges at even later time out of the hydrodynamic regime. And then the plateau is a super long time phenomenon that I won't talk about today. So the questions are, can we explain this observed random matrix universality and relate it to any other notion of chaos? The answer will be sort of yes, and we'll relate it to hydrodynamics. And then can we compute the Thoughtless time and this crossover from the hydrodynamic regime to the ramp regime? And again, the answer is yes. At least we have a formalism, and I'll show you a simple example. Okay. And of course, if you have any questions, please don't hesitate to stop me, but I'm gonna go ahead and go on, unless there's a question now. So the basic issue which separates the hydrodynamic regime from the ramp regime is that for, say, a local quantum chaotic system, there are a large number of slow modes. Think about hydrodynamic modes like the diffusion of energy or a sound mode. These modes all have a very slow decay. And so information in these modes lasts a long time. This collaboration is all about the flow of information. And that's what we're really asking, is how information in these modes, these special modes that remember the initial condition, how that information is slowly, on a hydrodynamic timescales, lost into the complexity of the Hilbert space. So to understand that, Mike and I, sat down to write down a theory of the generic properties of spectral form factor in any kind of Hamiltonian with slow modes. So here's how that theory looks. We're going to start with a model. So this is supposed to be very general, and then later we're going to apply this to a hydrodynamic system. But let's start with the general thing. Let's have a bunch of sectors, okay, labeled by alpha from 1 to omega naught. Omega naught is maybe a very large number, like e to the n. The Hamiltonian is something which is block diagonal between the sectors, that's h naught, and some perturbation v. And we want to know the spectral properties of this whole thing in terms of this block structure. So in a limit where we neglect v, if we assume, say, that each block, h naught, is itself chaotic, but they don't talk to each other, then because this is a variance, you just get a sum over all the blocks, right? You have a bunch of decoupled random variables, the variance adds, and so the spectral form factor is just the spectral form factor for a single block, a single chaotic random matrix, times a sum over, times the number of sectors at that energy, right? So if we want to take into account the effects of V, we need to include the possibility that V causes transitions between these different blocks. And because the spectral form factor is essentially a return amplitude, right? It's a trace in the time evolution operator. What we need to do is compute that return amplitude for the transitions caused by the perturbation V. So I'm going to write down an ansatz for the many-body wave function. The ansatz looks like the following. Suppose I start in sector alpha with particular state I. So sector alpha is a block of the Hilbert space, and I labels the state within that block. And I want to ask, if I started in that state and I evolved to time t, what does the wave function of the system look like? Well, the idea is I can be in one of any beta from 1 to omega naught of the sectors. I have some particular state here in that sector, and I can think of this state as normalized. And then I have a coefficient here, which I'll write as the square root of a probability to transition from sector alpha, which is where I started, to sector beta, which is where I end up. And the only reason why this is not a totally generic formula, why it's just not a rewriting of the wave function, is because I assume this probability here does not depend on the index I. Okay, that's the only assumption being made here. And so then the return amplitude is just the overlap of the initial state with the final state. And you see that's just the square roots of the probability from alpha to alpha times this particular factor here. Okay, it's not clear what this factor is, but that's what you get. So now the magic is you assemble the spectral form factor by summing these amplitudes and taking the square magnitude, then averaging at the end over disorder. So we just need one assumption, which is a very reasonable assumption, but it's an assumption. The assumption is that the averaging procedure, the disorder averaging, decouples the different sectors. So if you stare at this, I don't imagine you're going to get this in real time, but if you stare at this for a little bit, what you'll realize is that if you look at the alpha equals beta case here, in general, it's a sum over different alphas and betas. But if you look at the alpha equals beta case, then what you have is just the spectral form factor in sector alpha. Okay. And so as long as there's a delta function in alpha and beta, what you find is that spectral form factor for the whole system is just a sum over sectors. This filter function for the sector squared, right? One of the labels of the sector is certainly the energy. The return probability to go from the sector back to itself after a time t, times the spectral form factor within that sector. And in particular, if all the sectors are chaotic, well, then this spectral form factor of a given sector is just linear in time. It doesn't depend on alpha at all. And so all I need to do is compute the sum over return probabilities to calculate the spectral form factor. So that was all very abstract. Let me bring it down a little bit more concrete. Imagine you have a Hamiltonian, a local spin chain, say. You've broken all the other symmetries except energy conservation. And so on fairly general grounds, I mean, it doesn't have to be the case. You know, there could be localization, for example, but in fairly general situations, what you would expect is that you've broken all the other symmetries, you've broken translation symmetries, say, all you have left at very long times and long wavelengths is diffusion of energy. This is sort of the minimal slow dynamics in a local Hamiltonian system. So that's what I'm going to focus on from now on. And I claim that at time t, there's an extensive number of almost conserved modes. The reason being that a diffusive mode has an amplitude which decays like the diffusion constant times the wave vector squared. And so if I set that decay rate equal to 1 over t, all the modes of wave vectors lower than that characteristic scale have barely decayed. They haven't even decayed by 1e-fold yet. They're essentially the same as what they were at the start. So this is that characteristic wave vector here set by the time I'm looking at. And then you simply count the number of modes, which is just an integration over all the wave vectors less than this characteristic scale. And you see immediately that it's proportional to the volume of the system times this characteristic scale. So in other words, in any fixed time, there's an extensive number of modes that have barely decayed, right? So this is a lot of information left in your system that hasn't gone away yet. And then again, like I said, if each sector is random matrix-like, the spectral form factor would reduce to a product of this ramp plus a sum over all the return probabilities of these modes. And if these modes are all just diffusing, then we actually know how to calculate this. Here's an expression.
Sorry, Brian. So right now all of this is only relevant for times less than the Thoughtless time, right? That's what you mean by fixed time, that the time isn't scaling with system size?
Well, I mean, the Thoughtless time will come out, yes, but yeah, right now I'm saying that right now this time here is going to be much larger than 1 over system size squared. So I still have lots of modes.
Okay.
Yeah, good question. Thanks.
Yeah.
So here's the expression actually in the theory of linear diffusion for the amplitude of an energy fluctuation of wave vector k at time t in terms of the initial amplitude. And you see here that you just have a Gaussian centered around the initial amplitude decayed by a decay rate, which is just the diffusive loss. And it's a Gaussian with some width sigma. The width actually doesn't matter. But what we can compute easily enough from this Gaussian is just the integral over the initial condition. It's the integral over sectors of the return probability. That's the probability that the final amplitude is the same as the initial one. This is a straightforward calculation to do. You don't actually need to know the width. And you find that you just get this factor of 1 over 1 minus e to the minus gamma t. So again, this gamma is just k squared d, right? I write it down here. It's just the decay rate of the diffusing mode. So the sum over all the return probabilities is the product over all wave vectors times this factor. And in the quasi-continuous wave vector regime, you can simply do this product and you get a characteristic function of system size and time and some numerical coefficient that you can compute. And then to address Vedika's point, if you were to look at very long times long compared to the slowest decay rate in your system, then almost all of these terms are close to 1. And you can make a little estimate down here. You can say the sum of all return probabilities, if you want it to be 1 plus 2 times the dimension of space times epsilon plus order epsilon squared, then you can take the time t to be of order L squared times log 1 over epsilon. Okay, so this is just telling you, this is what I call a Thoughtless time now. If you want to be within epsilon of the random matrix result, which is 1, then you just need to take your time to be this epsilon dependent Thoughtless time. As I said, this originally was, this formula, when you substitute in d equals 1, was previously obtained in this paper here for this flow K circuit in the large Q limit, the large on-site dimension limit. And then they, rather reasonably just said, we expect this to be pretty general. They actually matched their finite size data and it looked pretty reasonable. What I'm saying here is this formula is totally general, at least as long as you restrict to the theory of linear diffusion, and it has a natural generalization to any dimension. You don't have to consider just diffusion. You could have subdiffusion, superdiffusion, etc. There are analogous formulae. So in the last couple of minutes, let me turn now to re-deriving this and extending this and putting in a more general framework of hydrodynamics, formal hydrodynamics. So what do I mean by formal hydrodynamics? I'm specifically referring to this closed time path formalism, which is basically a formalism that's set up to compute partition function-like objects where you have a state and you can evolve forward and backwards in time, possibly with different evolutions. Of course, when U1 and U2 are the same, this is just 1, and that's a very useful property. But by varying the fields, the background fields coupled to the forward and backward part of the contours, you can extract general properties of the system in terms of time order correlation functions, responses of various types. And this I won't really say much about this except to say that there's this beautiful whole formalism dealing with this problem. There are sort of 2 kinds of variables. Essentially, the idea is you integrate out the fast stuff and you keep the slow stuff. And then in terms of the slow stuff, you have some general rules that define the allowed space of effective actions. And there are kind of 2 important variables. There are R-type variables, which are symmetric between the 2 contours, and A-type, which are antisymmetric. And you have, again, some nice set of rules that govern this. Here's the simplest kind of example. You have a phi A and an epsilon. Epsilon is like basically the time derivative of phi R. These are your 2 variables. Epsilon is interpreted as the energy density. And you can think of, roughly speaking, if you focus just on the first term, phi A is like a Lagrange multiplier, which enforces a constraint that epsilon obeys the equation of motion of diffusion. And then there's this kind of phi A squared term. If you uncomplete the square, you do a sort of reverse Herbert-Hronovich trick. Then what you'll find is that this is basically telling you there's a random force in addition to this classical equation of motion. So this at the quadratic level is equivalent to stochastic diffusion of energy, linear diffusion of energy. So it kind of, at this level, it's just a fancy way of re-encoding something you already know. But the nice thing is you can include, for example, interactions and treat them in a systematic way. So here's the key assumption of our paper for this part, is that we want to take the effective action of the CTP formalism on this closed contour. You go out, connect, and come back. And we want to say, actually, that same effective action at the appropriate cutoff scale gives the relevant saddle point, the relevant contribution to the path integral, which computes this double contour thing, where instead of periodically identifying at the ends, you periodically identify the past and the future. In particular, we're going to assume the following 3 things. At a cutoff scale where the fast modes decouple, you have the same hydrodynamic action as in the CTP case, but with modified boundary conditions. You have time periodic boundary condition. We're going to assume that this modified action gives the dominant saddle point. And we also, again, need some averaging that justifies the fact that this action, the CTP action, connects the two contours, which are manifestly disconnected here unless you couple them some way. So in particular, the boundary condition in time, which is different, will mean that if you start integrating out the slow modes, start doing some of the path integral, the resulting infrared effective theory will look different than in the CTP case because you have this time periodicity. But at that short scale, we're assuming that they look the same because the fast modes are not able to effectively probe the periodic time circle, and so you can't, they don't change the story. So that's the key assumption. And just very quickly, first thing you can do is look just at the zero mode of this. So assume that you've waited long enough so all the finite momentum, all the finite wave vector modes have gone away. Then you can analyze the zero mode of this effective action here. It just reduces to phi a times the time derivative of epsilon. So it's basically phi a times the time derivative of the total energy. And what this just says is energy is conserved. And then when you do the path integral, there's an overall zero mode of the relative time phi a and the total energy epsilon. And whereas in this normal CTP formalism, the relative time between the two contours is fixed because you have this boundary condition where they're identified in the future. In this spectral form factor contour, they're not fixed. There's a freedom to integrate over the relative time shift. And that's exactly where the time factor T comes from. And then the integral over the total energy is just the integral over energy that we had previously. And I want to point out that it was observed already in Slide-Schenker-Stanford in the context of their SYK calculation that their result could be put into this form for the zero mode. But here we're saying, just start with hydrodynamics, and then the claim is this gives the right, if this gives the right saddle point, then you immediately get the ramp out. But you can do more. You can look at the finite momentum dependence, the finite wave vector dependence. Now you have, again, some full functional integral over the fluctuations of these A and R fields. You have this effective action, and just take my word for it, you can do the calculation and you exactly reproduce the formula that we had from this sort of general quantum mechanics argument. Okay, you exactly get this factor of the product over the decay rates. But as I said, the final nice thing I want to mention is that now you can in principle include interactions. There are always interactions in these theories. For example, if the diffusion constant depends on temperature, then an interaction arises because if you have a positive fluctuation of energy, the temperature is a bit higher. And so the diffusion constant is actually a bit different. So that means the diffusion constant itself is essentially epsilon dependent quantity. And so that induces nonlinearities in the theory. And I don't claim we've fully understood the problem here, but you can do some simple calculations of some simple new effects that occur because of the time periodicity. Basically, some of the usual rules of the CTP formalism are now violated because you have periodic time, because the past is not different from the future. And you can get some novel effects. And for example, in one dimension, you can compute a certain diagram that I showed in the previous slide. It generates a novel kind of self-energy. And it can actually modify the log of the coefficient from the diffusive expression I wrote before to some other more complicated thing in a certain regime of time. So again, I don't claim this is the total answer. And in fact, if you plug in the numbers, it doesn't look that different from the diffusive case for some reasonable system size and time. But in principle, interactions, at least in low dimensions, can actually strongly modify this ramp coefficient, or the way that the ramp is approached. Although the Thoughtless time, which is just about these very low-lying modes, is still the same. Okay, so let me wrap up. I think I'm pretty much out of time. The message for me is that quantum chaos in the spectral sense is sort of generic and robust. I almost want to claim that hydrodynamics implies chaos. This is not saying that just if you have diffusion of something, that means system is chaotic. We know that's not true. But if you have hydrodynamics in the sense of the general low energy, long time effective action of your system is this kind of hydro-like theory, which includes the conserved energy mode, then on seemingly pretty general grounds, if you have this assumption that this hydro action computes the spectral form factor saddle point, then you get immediately chaos in spectral sense, in the sense of the ramp coefficient being linear. Moreover, you see some nice things. For example, after the Thoughtless time, none of the variables are sensitive to the periodic time. And so then you recover some nice rules of the CTP formalism, like that expectations of A-type variables are always 0. And you can show that if you change the Hamiltonian a little bit from H naught to G to H naught plus G delta H, that variation of the spectral form factor is exactly one of these A-type variables. So in other words, in the regime where the diffusion constant is still relevant, this of course can change things because this can change the diffusion constant. But at very late time, after the Thoughtless time, this won't change anything because you have universality, or that's the expectation. And it's kind of predicted by this formalism because it's just an expectation of an A-type variable. So let me wrap up. I think what's interesting to me is that there's this growing number of connections between different manifestations of chaos, from hydrodynamics to eigenstate thermalization to random matrix theory. And, you know, we know they're connected. We have various examples of this, various model systems, et cetera, but I feel like there still is opportunity for a synthesis here. You know, what implies what really, you know, is guaranteed to happen, you know, how stable are things, these kind of questions. And the specific technical thing I told you was that we provided a set of tools to compute spectral form factors in systems with slow modes. These always occur in local Hamiltonians, so it's a natural question to ask. And we have some work in progress, nearly complete, applying this to symmetry breaking systems and glasses, but you can apply it to lots of other situations. And in terms of future directions, we think it's really exciting to try to connect to other effective theories of chaos. You can also ask, you know, what about longer times? Can I get the plateau from some hydrodynamic assumptions, or maybe some additional, you know, what additional ingredients do I need? And of course, the interactions are particularly interesting. It's really a kind of a, without being too grandiose, let me say it's sort of like a new kind of quantum field theory. We have periodic time. It still makes sense. It still seems to give sensible answers, but you have a whole host of new sort of physical effects within quantum field theory that are interesting to explore and understand. So yeah, thanks a lot for listening, and that's what I have to say today. Happy to have any questions if you have them.
Let's thank Brian then, and maybe we have time for like one quick question, and then we reserve the rest for the discussion session.
Hi, Brian. I have a question. I got lost how you derive the Thoughtless time, how you get the Thoughtless time, because my impression is that the hydrodynamic theory you developed is on the ramp, right?
It comes from, let me look at this slide.
Yeah, where the data of the decaying, initial decaying coming from.
So this formula here, which I'm circling with my cursor, can you see that?
Yeah.
That formula is totally general for this theory of linear diffusion. And these wave vectors k are discrete. So they come in multiples of 2 pi over L, where L is the system size, say, in one dimension.
Yeah.
So in the regime where so I can exponentiate this product to make it a sum, right, in the exponent. And in the regime where that sum can be treated quasi-continuously, I get this expression.
Yes.
Doing, you know, just integrating over this diffusion factor. But in the regime, if I go to very long times long compared to the lowest mode here, well, then I can't do that quasi-continuous approximation anymore. And so most of these things are now very close to 0. Or sorry, well, this factor here is very close to 0, so the overall thing is very close to 1. And so I'm multiplying a bunch of 1s together. And you just need to estimate, you know, how much those little small corrections can add up. And this is one crude estimate, like if you have the time longer than this time scale. So you see this L squared is the slowest mode, right? So if you go longer than the system size, the linear system size squared, which is basically the inverse lifetime of the slowest mode, and then you have this extra log epsilon helper, then you can guarantee that the sum over return probabilities is within epsilon of 1. So the Thoughtless time really comes from the basically just the lifetime of the slowest mode.
Okay, but here you have summing of R. But okay, the quantity summing over the return probability enters in your previous ansatz of the spectral form factor, right? If
That's
you go
right.
sides back.
So I had this formula right here.
Yeah.
So
this formula is during the ramp time, or it's valid from.
This formula is valid for all times.
Oh, okay.
All times beyond the time scale at which, say, well, as long as I have this decoupling assumption, it's valid. And if I also assume the spectral form factor of each sector is chaotic-like, then it's just valid for any time sort of, well, there's epsilons you have to worry about, but it's basically valid in the hydrodynamic regime and longer.
But this SFF alpha t is just the random matrix result. It's just
That's right. This is just the random matrix.
T.
It's like within a sector, you have only fast things, and those have all decayed. So it does look like random matrix theory within that sector. But it's only the sort of between sector correlations that are not random matrix like yet.
I see. I guess what I was confused is that my impression is like the spectral form factor competing is like the first order phase transition. It's like two classical saddle competing, right? You have the disk saddle and you have the connected saddle. But here it looks like you just have one saddle and you estimate its size. So that's what I'm.
Yeah, so that's what I think. That I think you can still have two competing saddles, but the time scale at which one saddle takes over from the other is still earlier than the time scale for these hydrodynamic modes to decay.
Maybe I can make a brief comment that the Thoughtless time is not the time where those saddles compete. The Thoughtless time is the time where the ramp saddle point approaches its sort of late time behavior, which is basically the same kind of thing that Brian was discussing here.
Okay. Thank you.
So in SYK, that's significantly later, is it, Douglas or Brian?
Sorry, what's the name later?
The ramp takes over before it reaches its late time behavior in SYK.
No, not late time. By late time, I mean the linear behavior. So
yeah,
there are exponentially decaying corrections to the linear behavior at early times with an extra coefficient of n. So in SYK, the Thoughtless time is when n times e to the minus t becomes small. So it's at a time that's like log n.
Yeah.
But this is that before or after the ramp takes over from the disk?
Well, it depends on exactly what you're computing, because the extent to which the disks, so if you do the simplest thing, then it's long before. But you can try to smear it in a better way so that the disks decay faster. That's something that
so the Thoughtless time would just not be seen at all in the like naive spectral form factor.
That's right. So you have to be a little bit more careful to try to see it by doing some kind of smearing.
So is that fair to say that Thoughtless time is when the particle excitation on the wormhole got decayed?
That's right.
Yeah. Okay.
But in the case of SYK, in the bulk, you have n different fields. So instead of a time of order 1, which is when the particle excitations would be small, you need the time to be of order log n, so that n times e to the minus t is small.
Sounds good.
Which particle excitations are you talking about? What's their origin?
These are like particles that are winding around the wormhole.
Yeah, I mean, like, if you have this contour, there's always some, even if you have a slow, even if everything is decaying rapidly, there's still some exponentially small correction, right? Which connects these two things. And in SYK, there is n of those.
It's like we should think of the wormhole as having a periodic direction that is linear in time. So it's like the effective temperature on the wormhole is decreasing in time, and the temperature is like 1 over the time. So the particles eventually are in a very low temperature state and basically in the vacuum. But at early times, before Thoughtless time, there's a significant amount of particle excitations.
Yeah.
But this is a Lorentzian period, or is it also somehow Euclidean period?
Well, it's a Lorentzian geometry, but the geodesic that goes around it is in the complexified geometry, and it has a
Euclidean length that's proportional to t.
The Euclidean length is proportional to the Lorentzian time, which is kind of funny.
Okay, that's very weird.
Huh. Yeah.
So maybe I would say for further questions for Brian, we can do that in the discussion session. So thank you, everyone. Nice questions. Thank you, Brian.